Okay, this is Math372 Complex Analysis, Lec09, Take 3. So when we ended class on Monday, we had an integral 1 over 1 plus x cubed. And so we're integrating this from 0 to infinity. And we got an answer that didn't quite match or did not appear to match what Mathematica was giving us when we plugged things in. So it turns out the answers were the same. But Mathematica was presenting the algebra differently. So we can calculate all integrals of this form, 1 over 1 plus x to a power. You can even ask, does it have to be an integer power? Could it be a rational power? Could we do something like that? Could we do an irrational power? So it's a nice exercise. See how far you can push this. See what kind of exponents you can put here. The challenge is then recognizing that you have a nice formula at the end of the day, is just seeing the algebraic simplification. So this is a good opportunity to talk about a technique you may have seen long ago in probably junior high. I think they called it like rationalizing denominators or expressions, something like that. Where they would, they would give like 3 minus 4 square roots of 2 over 5 plus 2 square roots of 7, and you would multiply by the right thing, and then the denominator would become nice, and the numerator would become messy, and this would be some kind of good form. I can't even remember anymore what kind of form they call this. But does this vaguely seem familiar? We want a technique to do something similar to that here and figure out exactly what this should be. So the answer we got was this was 2 pi I over z1 minus z2, z1 minus z3, and then 1 minus e to the 2 pi I over 3. And here, z1 was e to the I pi over 3, z2 was e to the I pi, and z3 was e to the 5i pi over 3. And so we plug all this in, and we have an expression. Let's assume, and it could be a strong assumption with me as your professor, but let's assume we have not made any algebraic mistakes in the analysis of this contour. You don't have to laugh immediately. You can at least wait a little bit before laughing. So let's assume we made no algebraic mistakes in the analysis of this integral. Okay? What can you tell me about our answer? What must be true about this integral? Has to be real. We can do better than just real. Positive, right? We're integrating a function that's non-negative from 0 to infinity. So if we wanted to, one way to find out what the value of this is, assuming we haven't made any algebraic mistakes, is just take the absolute value of this expression. So multiply it by its complex conjugate, take the square root. That will work. The other thing is to try to write down explicitly what's going on. And so we got z1, z2, z3. We were solving for the poles of 1 over 1 plus z cubed, right? So we wanted z cubed plus 1 equals 0, and we wrote that as z minus z1, z minus z2, z minus z3. Okay? So we've already got one way to check things, is we can multiply this by its complex conjugate, and then just do the algebra. So this is essentially cleaning up the denominators, cleaning up the expression. We can also factor this polynomial. How many of you have memorized the formula for the cubic? Good. Wikipedia, right? You can Google formula for cubic, and it will come out. There's an explicit formula. There's an explicit formula for the quartic. There's no explicit formula for degree 5 and higher. But this is degree 3, so one possibility is we could go through and use the cubic formula. There is another way to find roots. It's the method of divine inspiration. It's one of my favorite methods in mathematics, although it is sometimes hard to know when it will kick in. Usually exams is a good time for it to kick in, but it's not always something you can count on. If you know the answer, the problem is a lot easier. So if you just write down the answer, you're fine. So for those of you who've taken computer science, this is the difference between finding an answer and verifying an answer. It's often very easy to verify an answer for a problem. Does anybody know any roots of z cubed plus 1 equals 0? Negative 1. And in fact, that's this one over here. So we can write this as z minus 1, and that's going to be our root z2. And then we have z squared plus z plus 1. So yes, it should be z plus 1, thank you. Oh, and then if that's the case, then will this one become a minus 1? So let's see. This will give us a z cubed minus z squared plus z, and we'll have a plus z squared, a minus z, and a plus 1. So that works. So z cubed plus 1 is z plus 1, z squared minus z plus 1. If you did not know this factorization, this is factoring a cubed plus b cubed. How could you get this if you didn't know that factorization? Long division is acceptable. It's better to say long polynomial division, right? You might remember this from many, many days ago, and you'll put this polynomial, put this one here, and see how many times does z plus 1 go into z squared. That goes in z times. I'm sorry, z plus 1 go into z cubed plus 1. It'll go in z squared times. You could do polynomial long division and find this. Or you can go to a program like Mathematica and just have it do the division like this, have it factor the polynomial. A lot of times it will do stuff like this. All right, so we've got one root. So we have the root z2 equals negative 1. How do we find the roots of this? Quadratic formula. This is not going to have nice roots. I need two numbers that multiply to 1, and their sum has to be 1. Not going to happen. So the roots of this are going to be negative b, which is 1, plus or minus the square root of b squared, which is 1, minus 4ac all over 2. So we get 1 plus or minus the square root of negative 3. So we get 1 plus or minus I square roots of 3 over 2. And so we have explicit formulas for all of these. We can plug them in. And then the question is, will this lead to easier algebra? Is it better to do something like this? I mean, it's really all the same. It's just trying to find a way to do the expressions at the end of the day. Mathematica has a lot of nice features. Some of the features you can use, you can have it take the absolute value of an expression. You can have it take the real part of an expression. You can have it take the imaginary part of the expression. When I told Mathematica to take the absolute value of this and the real part of this, they were the same. And the imaginary part was 0, which is exactly what you would hope for. And so at the end of the day, the final expression came out to be 2 pi over 3 root 3. Does that seem a reasonable answer, 2 pi over 3 root 3? It's positive. It's real. All right, so let's make a list of good things about this. 1, it's positive. 2, it's real. I'm going to think of 2 other things that are nice about this.
Incredibly simple.
It's incredibly simple. So what I'm thinking is related to that, it's simple. I would say it's beautiful. What is nice about this? Or what does it depend on that you think might actually be reasonable now with complex analysis? There's a pi. So we'll say beautiful. It's also a nice simple expression. It is not this complicated massive formula. There's one other thing which is nice about it. It's smaller than pi. And then there's one other thing I need. And it's larger than pi over 2 root 2. Am I doing it right? Yeah. So where are those coming from? Yeah, this is the integral from, oh, I've got to be careful. So here, I think I would want pi over 2. 1 over 1 plus x squared. And so here, I might actually, and then this would be the integral from 0 to infinity of 1 over 1 plus x to the 4th. Because we know 1 over 1 plus x cubed, it's always going to be smaller than this integrand, and it's always going to be larger than this integrand. I have not checked actually to make sure that these algebraic expressions are going in the right way. I'm just hoping right now. But we know the even ones. The even ones were much easier to do. And the answer should be sandwiched somewhere in between. It seems very likely that we should have a formula like this because we're going to have some kind of expression involving the roots. And I'll leave it to you as an exercise to figure out, should there be a nice expression involving all the roots? Or the roots that are in the contour. So if you want, for extra credit, so prove a nice formula for the integral minus infinity to infinity of dx over 1 plus x to the 2n. So you are not allowed to search for this on the internet. You are allowed to talk with each other. So standard honor code stuff applies. Whenever you do anything in this class, I strongly encourage you to work with each other. You're fine to normally use resources on the web. You just have to state when you use something. Given that this is extra credit, don't go online and find the answer online and submit that. But can you find a clean formula for this? Do you think a clean formula exists? How many of you have ever done a physics lab or a chemistry lab to gather data? Okay. How many of you have ever done a math lab to gather data? Okay. How do you think you would do a math experiment on this integral? Yeah, run it a bunch of times. You could use Mathematica to integrate this for various choices of n, right? Gather some data. You might actually start to notice a pattern. And so see if you can do something like that. And then, if you see a nice pattern, that can often help you enormously in terms of figuring out what to prove. So whenever possible, you want to gather data about what's going on. It's not always possible. Mathematica is a wonderful tool. I've got to be careful because this is recording. But there are sometimes, it's either pronounced bug or features, depending on who you talk to. So you cannot always be confident about the answer you're getting. If you really care about the answer, if the answer is truly important, people often run it either on 2 different systems, or you do it in something that's open source where you can actually see the algorithm that's being used. So a lot of people in mathematics like to use something called Sage. Sage is open source. If you want to know what algorithm is being used, you know. Mathematica has some proprietary black box algorithms. And so it's not always clear what's being done. Okay. So, some of that algebra you did all those years ago is now somewhat useful. The rationalizing denominators, the polynomial long division. There is a reason. I don't know if they ever told you at the time why you were doing this, other than, well, this seems to be in the curriculum and we're going to have a test on it. But there is a reason for these algebra tools. It is often exceptionally difficult to notice that 2 things are the same. Did I tell you the Kepler story, or was that in 4.6? Okay, so think of the Kepler story where he had it was an ellipse, but did not recognize that it was an ellipse. So you are welcome, of course, to use things like Mathematica to do a lot of these algebraic simplifications and see, is there a nicer way of writing what you have? All right, can I borrow your book for a moment? All right, so there was a request to do problems. So let's put me on the spot, or better yet, let's put us on the spot. So let's evaluate the integral from 0 to infinity e to the ax with a minus sign. Do you guys prefer cosine or sine? Cosine bx dx. And it says, by integrating e to the minus az, a equals the square root, okay, of a squared plus b squared sector with angle omega such that cosine of omega equals a over a. Okay, thank you. So the first thing when you have something like this is, we're fortunate that there's a hint. So the hint is telling us exactly what to look at and what sector to do. So when you have something like that, it makes it a lot easier. Why is this a natural thing? We could have done the integral from 0 to infinity e to the minus ax sine bx dx. Right? That was the other thing we could have done in the problem. Is there any way we maybe could do both of them at the same time? Yes?
You could make one be like, one might be the real part of it.
Ah, so one of them looks like a real part, one of them looks like a complex part. If I replace the or with a plus I, if I evaluate this integral, this is real, this is now purely imaginary. So if I evaluate this integral, the real part of that is just this, the imaginary part is just that. And so if I do that, I'm now studying the integral from 0 to infinity e to the minus ax e to the I dx dx. How many of you have taken some physics and seen Fourier transforms? There are at least 3 different definitions of the Fourier transforms. Some people like to use 2 pi up here. Some people don't. Some people try not to piss anybody off, and they have like a square root of 2 pi outside to try to hedge their bets depending on who's looking at their stuff. Depending on what you're looking at, different definitions are a little bit better than others. This is essentially the Fourier transform of the function e to the minus ax. And this function, we want this function to be 0 for negative values of x, because otherwise it would be exponentially blowing up. So when I saw these, the first thing that came to my mind was that we really have half of a problem. I'm not making your life easier by telling you, let's only do the cosine part. I'm actually making it harder for you by hiding the fact that there's a corresponding piece. So frequently, if you look at things the right way, it's much easier. Now, if I look at this, can you begin to see where the big A comes from? This is now the integral from 0 to infinity of e to the minus a plus ib x dx. So we would need to choose a function f of z. I just want to make sure that they're saying just a is the square root of a squared plus b squared. So a is just the real part of this. Okay. I'm sorry?
Oh, you mean little a is the real part? Is that right?
No, I'm sorry. I mean a is the modulus of a plus ib.
Okay.
And so they're telling us to look at the function e to the minus az. So they are suggesting we look at this. And a is the square root of a squared plus b squared. So it's the length of that quantity here. So this is where it's sometimes a little bit harder to think of what we should be looking at. One of the things that's nice about this is now if we go along the real axis, this will be e to the minus ax. This will be something that's pure real. Okay? So we need to figure out what the contour is. And they say choose an angle omega such that the cosine of omega is a over a. So if we think about our triangle, here is a, sorry, a would be down here. And this would be b, and this would be the square root of a squared plus b squared. And that would be the angle omega. So it's suggesting that we look at a contour like this. So here's 0, here's R, and now we've got to figure out what would that be. This would be part of an E. So that would be like that. Okay. So do we have any poles for our function, e to the minus az? No. So the real question is going to be, how is this going to all relate to the integral we need to do? And is it going to be small in certain places? Where do we hope that this is small if we've chosen the right contour? Yeah, it's got to be small in the semicircle or we're in real trouble. So what would be going on there? So do you think it's going to be small on the semicircle?
We might have to split it up into two sort of parts along the semicircle.
So one possibility is that, but let's look at e to the minus az. And on the semicircle, we know, well, how can we write z on the semicircle?
E to the I. R e to the I. Yeah.
R e to the I theta.
Yeah.
0 less than equal to theta less than equal to omega. So we can write z as r cosine theta plus I r sine theta. So e to the minus az is e to the minus ar cosine theta, e to the minus air sine theta. So the absolute value of e to the minus az on the semicircle is just e to the minus ar cosine theta, because this part has absolute value 1. What can you tell me about this?
Why does the second part have absolute value 1?
Because it's e to the minus real number times I. It's something to a pure imaginary number. E to the I phi has absolute value 1. So this has absolute value 1. So we're left with this quantity over here. So why does it decay? Yeah, cosine theta is bounded. This is, so the worst case for us is at cosine omega. So this is less than or equal to e to the minus a cosine omega to the r. So this is decaying really fast. Okay? So we have exponential death here. This is just some constant. This is 1 over. So if you want, this is equal to 1 over gamma to the r for some gamma greater than 1. Because e to the, this is 1 over e to the a cosine w omega. E to the 0 is 1. Anything a little bit larger than that, and you'll be a little bit greater than 1. So gamma is e to the a cosine omega is strictly greater than 1. So this is decaying exponentially fast. So even if I multiply it by, can somebody bound the length of the arc? Okay. Yeah, you're doing too much work. 2 pi r, right? The length of the arc is no more than the length of the whole circle, right? We're not going to be winning by a constant. We're not going to be that delicate of an analysis. And so we know the contribution over the semicircle is less than or equal to, under the absolute value, 2 pi r divided by gamma to the r. And that goes to 0 really fast. So we know that there will be no contribution over that arc. This doesn't mean that we found the right arc to look at. This doesn't mean we found the right contour to look at. It just means if we were to choose this contour, then the contribution over this part over here is negligible in the limit. We always like something like that. If we actually had to do an integral like that, that would be a terrible integral to have to do. So now we're left with the other two integrals. Okay? Are you a little bit worried? You know, that we may not get the answer we want. Because when we integrate over the bottom, we're just going to get something that's completely real. But maybe when we combine these things, these two pieces will somehow combine in such a way to give us what we want. Are there any poles of this function? This function has no poles, right? So by Cauchy, it's got to integrate to 0. All right, so let's see what happens. So are we all okay with the semicircular part? Okay. So let's call this gamma 1, gamma 2, gamma 3. We know 1 over 2 pi I integral over gamma 1 plus integral over gamma 2 plus integral over gamma 3 of e to the minus az dz equals 0. And we know in the limit this goes to 0. So we can drop the 1 over 2 pi I, and we're just left with the other two integrals. So we're left with the integral from 0 to infinity of e to the minus ax dx. This is the gamma 1 piece. And then the gamma 3 piece, where do I go from now?
R to 0.
Right, but now we're taking things in the limit. So it'll be infinity to 0. So it'll be e to the minus a, and now here, x is going to be, I think it's just going to be x e to the I omega. Because here, z is equal to x e to the I omega. dz will be e to the I omega dx. Slightly worried, but somewhat optimistic that things are going to cancel out and reinforce. You know, right now we just have everything equals 0. It would be nice to have something that will lead to an integral we can do. Are there any integrals here we can do? Yes, we can actually integrate this one. So sometimes you have to stop and remind yourself, oh wait, I already know how to do this. I don't need to use complex analysis. This is a Calc 1 integral. I'm integrating e to the minus ax. So the inspiration for this problem is, we're looking at this nasty integral over here, which has a mix of both a real and an imaginary part in the exponent. And the idea is, let's replace this with an integral that's nice on the real axis that we can do with other techniques. And then what we'll get on the other part will be the part we want. So this is a little bit different than all the other problems we've been looking at. In all the other problems we've been looking at, what we want is positioned right on the real axis. And then we use the other parts to figure out what it is. Here what we're doing is we are starting with something on the real axis that we know, and using that to get something in another place. Okay? So now that we have this, now we just have to figure out the integration. Okay, so now this integral is e to the minus a. So I need an a, I need a 1 over a. The minus sign flips the order, and I'll just get 1 over a. Everybody happy with that? Now this one, I want to flip the order of integration. That's going to cost me a minus sign. Right? Well, if it's minus, let's bring it over to the other side. So that will equal the integral from 0 to infinity of e to the minus ax. Now, e to the I omega is cosine omega plus I sine omega And then we'll have e to the I omega dx. Okay. Anybody know a way to simplify the exponent here? Where are a and omega connected? Oh!
Cosine of omega is just
So if we call this a, then a cosine omega is little a, and b is a sine omega. So we have an e to the I omega over here. Does this depend on x? Let's bring it over to the other side. So we have the integral from 0 to infinity of, this is going to be e to the minus ax, e to the minus, I think, ibx dx equals e to the minus I omega over a. Is that what we wanted to integrate? It's almost. The real part, so the real part of this is just going to be what we want, because the real part will be a cosine. The imaginary part will have an extra negative sign. Not a big deal. Yes?
Why is there a negative now on the I?
We have to bring this over to the other side, right? Or over here? We had a minus a.
No, sorry, yeah. It was the first thing you said.
Okay. Okay. So the real part is going to be the integral from 0 to infinity of e to the minus ax cosine bx dx. And then that should be the square root of a squared plus b squared. And now we need the real part of this. So this is cosine omega. And what's cosine omega? Little a over big A. So we lose the square root down below. And we should get the following. So we will see if Mathematica can handle this. We were integrating exponential negative ax cosine bx. X goes from 0 to infinity. So it is thinking right now. There is a way in Mathematica to print something called assumptions. What should we be assuming about A and B? Do we need to assume anything about A or B for this integral to make sense? So it's written in the book, but the first thing you always want to make sure is, do the integrals make sense? Over here, A is positive, so everything is fine over here. But if I'm looking at this expression, if little a is negative, this integrand is not decaying. So I need little a to be positive. B doesn't really matter, because B is just going to be inside a cosine. So the expression it gets is, if the absolute value of the imaginary part of B is less than the real part of A, it's a over a squared plus b squared. Right, given that the imaginary part of b is 0, and a is a positive number, then that will give us then 0 is less than real part of a, so a has to have positive real part. So what they're saying is actually the answer will hold a little bit more generally. Ooh, this provides an interesting opportunity to talk about analytic continuation. This is a nice function in A. Let's fix B. If I change a by a little bit, if I add a small imaginary part to a, is this integral still going to be nice? What do you think? Do you think this integral will still be nice if I replace a with a plus a small imaginary number? Is it going to change the integration from existing?
Would visually that just be like shifting that contour map slightly off the
Well, shifting a by a small imaginary part would actually be shifting b. Right? Because if I put in plus I something, I can just change b to like a b prime. So do we agree that if we change a by a little bit, this integration should still be nice and should still be an answer? Do you think this integral is complex differentiable as a function of a? We know that equals a over a squared plus b squared if a is real and positive. Maybe if the real part of a is positive, this will still hold. So if you can show that this function is holomorphic for a real part of a greater than 0, we know it equals this when the imaginary part of a is 0. So we have two functions that are identical when the imaginary part of a is 0. Ooh, what theorem is this? Yes. What's the key word? We haven't said analytic continuation. We said something else. We said a sequence of points. Not the residual. Accumulation. If we have two functions that agree on a sequence of points that accumulate, then they must be identically equal. We proved this result for the real part of a positive. Maybe we could shift things a little bit and give a an imaginary part. And because they would accumulate along imaginary part of a equals 0, they have to be identically equal. In fact, that might even allow us to just say maybe we can just take the case when b equals 0. So I'll leave this as things for you to think about, that there's a lot going on in this problem. This is a really interesting problem. We got decays in many different ways. We noticed what was going on here is because there was a limit to how close we got, here's the angle omega. The cosine of omega was a positive number, so we had exponential decay. If we had to integrate all the way up to being on the y-axis, there would be no exponential decay going straight up. And we would probably have to say, let's go a small little bit of an angle there, do that separately, and then do the exponential decay elsewhere. So you always want to look and see where's your decays. The challenge here is figuring out what contour and what function. This was the first time where it's not clear what function to look at. Is instead of looking at the function that we started with, we changed it a little bit, and now it was on the diagonal part that where we wanted to merge. Question?
So the two functions that you're looking at that would be the same along that line are when
Would be this integral?
that one when the real part is or the imaginary part is 0 for a, and that same one where a has like
Right. So if we wanted to label our two functions, we could say, f1 of a is the integral from 0 to infinity of e to the minus ax e to the I bx dx. And we could say f2 of a is a over a squared plus b squared. And we know if the imaginary part of a equals 0, that implies f1 of a equals f2 of a. So these functions agree on a set of points that accumulate. So if this function is complex differentiable, then we have two holomorphic functions that agree, so they must be identical in their common region. And we might then be able to just replace a with maybe a plus I a prime, something like that. We need to keep the real part of a positive. Okay. So, I hope this gives you some sense of the power of complex analysis, but also that there's an artistry here. It is somewhat challenging at times to figure out what you're looking at. All right, so you've got about 5 minutes left. Let me just start with some definitions that will prepare us for the next class. So, types of singularities. So we have removable, we have pole, and we have essential. They are listed in order of increasing severity. A removable singularity, what do you think you can do to it? Yes. Every now and then we choose good names. Okay? I can't even make myself write this down on the board. Let's consider f of z is z minus 1 over z squared plus 1. Okay? Trouble at z equals minus, did you write?
You mean z squared minus 1.
I mean z squared minus 1. Trouble at z equals 1. So when I put in z equals 1, the denominator blows up. Oh no. Well, we can write this as z minus 1 over z minus 1 z plus 1. If you cannot hear it screaming at you, please cancel the z minus 1 in the numerator and denominator. You need to have your ears checked. Okay? You've got to be able to hear this. Right? And so if we cancel these, then we get 1 over z plus 1. And now we know how to define the function at z equals 1. Make it 1/2 at z equals 1. So then the question is going to be, under what conditions will you have something that's removable? Okay? Here it's quite clear that this is going to be a removable singularity. This singularity is really not there. If I write it, if I factor it, if I clear out the z minus 1, we see that as the limit exists as we approach, it's approaching 1/2. Let's just define the function to be that. Everything will work out. So pole, pole of order n at z0 means reciprocal has a 0 of degree n at z0. So here what we'll mean is f of z is a minus n z minus z0 plus a minus n plus 1. This is to the minus nth power, z minus z0 to the minus n plus 1. Here's our expansion. I can pull out the z minus z0. I can even pull out the a minus n. And then I'm going to be left with 1 plus blah. And the blah is going to be something z minus z0, then something z minus z0 squared, then something z minus z0 cubed, etc., etc., etc. If z is really, really close to z0, what does blah look like? 0. I can invert this. And so 1 over f of z is going to be 1 over a to the minus n, z minus z0 to the n, 1 plus blah inverse. And that'll be fine. And then you'll see that this function will have a 0 of order n. So the big thing here is for a pole, it stops at a finite point. So for an essential singularity, that's going to be worse than removable, worse than pole. What do you think might be an essential singularity? Everything else. So we'll leave that for now. and we'll try to figure out what does everything else mean. So here is a terrific function to study, e to the 1 over z, which is a sum and goes from 0 to infinity of 1 over n factorial 1 over z to the n. For what values of z does this function converge? It converges for every z but 0. So OK if z does not equal 0. What should we put in? Is there any way to make sense of this as z equals 0? So when we look at what's going on, if we have a pole, as z approaches z naught, it's going to look like 1 over z minus z naught to the n. What can you tell me is going to happen if I have a pole? What happens as I approach z naught? It's going to blow up. Now, it might blow up in different ways. It might blow up as a real number. It might blow up as an imaginary number. So if I give you f of z is 1 over z squared. As z goes to 0 through the real numbers, it goes to 1 over 0 squared, goes to infinity. What if I go through along the imaginary numbers? If I write z is iy, y goes to 0 through the positive numbers, then I'll have 1 over negative y squared. That will go to negative infinity. So the magnitude is exploding, but it's not necessarily exploding in the same direction. Now, I do have a minute. Here is a sphere. What we sometimes do is we look at what's called the one-point compactification of the complex plane. So those of you who have seen some topology before, we put the complex plane down in the equator. We take the north pole over here, and we plant the infinity flag. And you give me any point in the plane, and I draw a line from your point to the north pole. And it will hit the sphere in one and only one point. If it's outside the equator, it will hit it on the surface of the sphere up top. If you're inside the equator, it will hit it on the surface down below. Every point on the sphere is hit but one point. What is the one point that's not hit? The infinity. And notice that as you get further and further away from the origin, all of your points are mapping closer and closer and closer to infinity. So in this sense, we mean infinity is a neighborhood. And all of these different explosions are all in the same neighborhood of infinity. So there's some really nice topology going on here. That we're adding one point, the point at infinity, and all of these points very, very far away are close to it. If you look at the reciprocal of all these points, they're all very close to 0. So the neighborhood of infinity, well, just take the reciprocal of everything, and that's talking about the neighborhood of the origin. All right, so this is a good place to start. A essential singularity will have very different behavior. And we will see some strange things. All right.